Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. 3.5 billion years ago, an observer looking at both Earth and Mars might have seen striking similarities. Two blue worlds, both harboring vast oceans, thick atmospheres, and possibly even the sparks of primitive life. Today, these planetary siblings couldn't appear more different. Earth remains a vibrant blue marble, while Mars has transformed into the dusty red desert we now recognize. The story of how these twin worlds diverge so dramatically reveals fundamental principles of planetary science and offers crucial insights into Earth's own remarkable stability. Recent evidence from orbiting spacecraft, landers and rovers has confirmed what scientists long suspected. Mars once hosted abundant liquid water. The Mars Reconnaissance Orbiter has mapped extensive networks of ancient riverbeds, deltas, and shorelines etched into the Martian surface. The Curiosity and Perseverance rovers have analyzed sedimentary rocks formed in lake environments, while instruments aboard these missions have detected hydrated minerals that could only form in the presence of significant amounts of liquid water. Most compelling are the massive outflow channels that scar the Martian landscape, suggesting catastrophic floods of almost unimaginable scale. Measurements indicate that some of these channels carried volumes of water equivalent to the Mississippi River, but flowing approximately 1,000 times faster. These features paint a picture of a planet that once hosted an ocean, covering roughly 20% of its surface, containing enough water to form a global layer approximately 450 meters deep. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. Yet today, Mars exists in a state of profound desiccation. Its current water inventory consists primarily of frozen reservoirs, polar ice caps, subsurface permafrost, and tiny amounts of atmospheric water vapor that occasionally condense as thin frost or high-altitude clouds. The transition from a water-rich world to today's frozen desert represents one of the most dramatic planetary transformations in our solar system. Understanding this transformation requires examining the critical planetary systems that regulate surface conditions. Both Earth and Mars began with certain advantages and disadvantages imposed by their formation and positioning in the solar system. Mars, being smaller and farther from the Sun, faced significant challenges from the start. With approximately half Earth's diameter and 1/10 its mass, Mars possessed less internal heat and weaker gravity. Its more distant orbit placed it about 50% farther from the Sun than Earth, receiving less than half the solar energy. Despite these differences, early Mars managed to sustain conditions remarkably similar to Earth's for hundreds of millions of years. The evidence suggests a warmer, wetter epoch, during which liquid water flowed across its surface, carved valleys, filled lakes, and accumulated in at least one major ocean concentrated in the northern hemisphere. This period, spanning from approximately 4.1 billion to 3.7 billion years ago, coincides with what we call the Late Heavy Bombardment, a time of intensive asteroid and comet impacts throughout the solar system. What changed? How did two worlds with oceans and atmospheres take such different evolutionary paths? The answer lies in a complex interplay of geological, atmospheric, and astronomical factors, a planetary science mystery that reveals the delicate balance required to maintain a habitable world over billions of years. The forces that stripped Mars of its most precious resource offer profound lessons about planetary fragility and resilience, lessons that may prove crucial as we contemplate humanity's future, both on Earth and beyond. Mars emerged from the protoplanetary disk approximately 4.5 billion years ago, during the same period of intense formation that produced Earth. However, crucial differences in its development set the stage for its eventual transformation. The red planet formed with approximately 53% of Earth's diameter, resulting in just 15% of Earth's volume and only 11% of its mass. These seemingly modest differences in physical dimensions would have profound consequences for Mars's long-term ability to retain its atmosphere and water. Planetary scientists at institutions like NASA's Goddard Space Flight Center have determined that Mars's smaller size meant it cooled much more rapidly than Earth. Think of planets like cosmic potatoes. Larger ones stay hot inside longer. Earth, with its substantially greater volume, retained more of its primordial heat and continued to generate significant internal heat through radioactive decay of elements like uranium, thorium, and potassium. Mars, with its smaller reservoir of these heat-producing elements and greater surface-to-volume ratio, experienced accelerated cooling. This rapid cooling had cascading effects on Mars' geological systems. Analysis of Martian meteorites reveals that the planet's core solidified much earlier than Earth's. While Earth maintains a partially molten outer core that generates our protective magnetic field through the dynamo effect, Mars's dynamo shut down within the first 500 million years of its history. The evidence for this early magnetic field remains preserved in certain ancient Martian rocks, which show magnetic orientation patterns similar to the magnetized stripes found on Earth's seafloor. The Mars MAVEN, Mars Atmosphere and Volatile Evolution mission, launched in 2013, was specifically designed to investigate the consequences of this early magnetic field collapse. Data from MAVEN indicates that without a global magnetic field, the Martian atmosphere became directly exposed to the solar wind, a stream of charged particles continuously flowing from the Sun at speeds averaging 400 kilometers per second. This merciless bombardment gradually stripped away Mars' atmosphere through a process called ion sputtering, where solar particles transfer their momentum to atmospheric molecules, allowing them to escape the planet's gravitational pull. Evidence supporting this atmospheric loss mechanism comes from several measurements. The current Martian atmosphere is enriched in heavier isotopes of elements like oxygen, carbon, and hydrogen compared to their lighter counterparts. This isotopic fractionation occurs because lighter variants escape more easily, leaving the heavier versions behind, similar to how a sieve captures larger particles while smaller ones pass through. The ratio of deuterium, heavy hydrogen, to regular hydrogen in Mars' atmosphere is approximately 5 times higher than on Earth, providing a clear fingerprint of extensive atmospheric loss. Another critical disadvantage for Mars was its distance from the Sun. Positioned at 1.5 astronomical units from our star, compared to Earth's 1 AU, Mars receives just 43% of the solar energy per unit area that Earth does. This reduced solar flux meant that Mars' climate operated with a smaller energy budget from the beginning, making it more susceptible to cooling as atmospheric conditions changed. Additionally, Mars's more elliptical orbit introduces greater seasonal variations compared to Earth. While Earth's distance from the Sun varies by only 3.4% throughout the year, Mars experiences a fluctuation of approximately 19%. This orbital eccentricity subjects Mars to more extreme seasonal shifts, complicating any natural stabilizing mechanisms that might have preserved moderate surface conditions. Perhaps most consequentially, Mars's smaller mass means its gravitational pull is just 38% of Earth's. This weaker gravity made it fundamentally easier for atmospheric gases to achieve escape velocity and drift into space. The threshold for atmospheric retention depends on both temperature and the mass of gas molecules. Lighter gases require less energy to escape. Calculations show that, even in the absence of solar wind stripping, Mars would struggle to hold onto hydrogen and water vapor over geological timescales, especially during periods of increased upper atmospheric temperatures. These initial disadvantages created what planetary scientists call a vulnerable system, one lacking the robust self-regulating mechanisms that would allow it to withstand perturbations and maintain stable conditions over billions of years. Mars began with cards stacked against it, but the planet's transformation from wet to dry wasn't immediate. The evidence suggests that liquid water persisted on Mars for hundreds of millions of years, indicating that additional factors must have contributed to its eventual desiccation. The most consequential distinction between early Earth and Mars may have been the longevity of their magnetic fields. Earth's magnetic field, generated by the churning motion of molten iron in its outer core, has persisted for at least 3.5 billion years and likely much longer. This invisible shield extends tens of thousands of kilometers into space, forming a protective bubble called the magnetosphere that deflects the solar wind and prevents atmospheric erosion. Mars, by contrast, lost its global magnetic field early. Evidence from the Mars Global Surveyor mission revealed that while parts of the ancient southern highlands still retain magnetized rocks, proof that a dynamo once operated, this field collapsed approximately 4 billion years ago. The timing couldn't have been worse, as this magnetic shutdown coincided with a period when the young sun was more active, emitting more intense ultraviolet radiation and stronger solar winds than it does today. The consequences of this premature magnetic failure were profound. Without magnetospheric protection, Mars' upper atmosphere became directly exposed to solar particles traveling at supersonic speeds. When these charged particles collide with atmospheric molecules, they can transfer enough energy to accelerate them beyond Mars's escape velocity. Instruments aboard the MAVEN spacecraft have directly observed this process in action, measuring the rates at which oxygen, carbon dioxide, and other atmospheric constituents are currently being stripped away. The loss rates quantified by MAVEN are modest by current standards, approximately 100 grams of atmospheric gas per second, but extrapolated over billions of years, they account for the removal of a substantial atmosphere. More importantly, scientists believe these rates were significantly higher in the past when the sun was more active. Models suggest that during solar storms, which were more frequent and intense early in solar system history, atmospheric escape rates could increase by factors of 10 to 100. The loss of the magnetic field removed the primary shield protecting the Martian atmosphere, explains Dr. Janet Luhman of the Space Sciences Laboratory at the University of California, Berkeley. It's comparable to removing Earth's ozone layer. Suddenly, the atmosphere is exposed to processes that can break it down much more efficiently. Beyond direct atmospheric stripping, the absence of a magnetic field allowed increased penetration of solar ultraviolet radiation to Mars's surface. This energetic radiation can break water molecules into their constituent hydrogen and oxygen atoms through a process called photodissociation. Once separated, the lightweight hydrogen atoms can easily escape to space, effectively removing water from the Martian system one hydrogen atom at a time. The critical importance of magnetic protection becomes apparent when we compare Mars to Venus, Earth's other planetary neighbor. Venus, despite being closer to the Sun and subject to more intense solar radiation, has maintained an atmosphere 92 times denser than Earth's. This seeming contradiction is partly explained by Venus's slightly stronger gravity compared to Mars, but also by other factors, including possible remnant magnetism and its dense atmosphere's own ability to resist solar wind erosion through induced magnetic effects. Earth's continued magnetic protection represents one of our planet's most fortunate features. Paleomagnetic studies of ancient rocks demonstrate that Earth's magnetic field has persisted throughout geological history, though not without fluctuations and occasional reversals in polarity. During these reversal events, which can take thousands of years to complete, the field weakens substantially but never disappears entirely. Even today, Earth's magnetic field continues to protect us from atmospheric erosion. Satellite measurements have detected what scientists call a polar wind of hydrogen, oxygen, and other atmospheric constituents streaming away from Earth along open magnetic field lines near our poles. Without our magnetosphere, calculations suggest Earth could have lost a significant fraction of its oceans over geological time. The magnetic dichotomy between Earth and Mars represents a crucial lesson in planetary habitability. Internal geological activity doesn't just affect a planet's surface through volcanoes and plate tectonics. It provides essential protection from the harsh space environment. As we search for potentially habitable worlds beyond our solar system, the presence or absence of a magnetic field may serve as a key indicator of a planet's long-term ability to sustain surface water and potentially support life. When examining why Mars lost its water while Earth retained its oceans, we must consider the critically important role of atmospheric composition. Both planets initially formed with what scientists call secondary atmospheres, gas envelopes, derived from volcanic outgassing rather than captured directly from the solar nebula. However, the specific mixture of gases each planet developed would prove consequential for their thermal regulation. Earth established a nitrogen-dominant atmosphere with significant quantities of carbon dioxide, water vapor, and other greenhouse gases. This atmospheric cocktail provided efficient heat trapping through the greenhouse effect, a process where certain gases allow sunlight to pass through but absorb the infrared radiation that would otherwise escape to space. Without this natural greenhouse effect, Earth's average surface temperature would be approximately 33 degrees Celsius colder, leaving our planet largely frozen. Mars, despite extensive early volcanic activity evidenced by massive formations, like Olympus Mons, the largest volcano in the solar system, failed to develop and maintain a similarly effective greenhouse atmosphere. Analysis by rovers and orbital spectrometers reveals that Mars' atmosphere evolved differently, becoming progressively thinner and dominated by carbon dioxide, which currently makes up approximately 95% of its tenuous air. The Mars Curiosity rover's sample analysis at Mars, SAM instrument, has detected isotopic signatures in rocks, suggesting that Mars once had a much thicker carbon dioxide atmosphere, potentially dense enough to maintain temperatures above freezing through greenhouse warming. However, unlike Earth, Mars lacked robust mechanisms to cycle and regulate its atmospheric carbon dioxide over long timescales. Earth's carbon cycle represents one of its most important climatic stabilizing mechanisms. Through weathering processes, atmospheric carbon dioxide dissolves in rainwater to form carbonic acid, which reacts with surface rocks. These reactions sequester carbon in carbonate minerals and eventually transport it to the ocean floor. Later, through plate tectonics, these carbonates can be subducted into Earth's mantle, where they melt and release carbon dioxide through volcanoes, completing the cycle. This system operates as a thermostat. When Earth gets warmer, weathering accelerates, removing more carbon dioxide and cooling the planet. When conditions cool, weathering slows, allowing carbon dioxide to accumulate and warm the planet. Earth has this remarkable self-regulating system that's been maintaining habitable conditions for billions of years, explains Dr. Bethany Illman, planetary scientist at Caltech and JPL. It's not just having the right ingredients, it's having the right processes to cycle and maintain them. Mars, lacking active plate tectonics, couldn't recycle its carbon or maintain this regulatory system. Instead, three primary processes depleted its atmospheric carbon dioxide: space weathering, direct loss to space through solar wind stripping; chemical weathering, forming carbonates without recycling; and polar sequestration, freezing of carbon dioxide at the poles. Evidence for carbon sequestration comes from orbital spectrometers that have identified extensive carbonate deposits in certain Martian regions, particularly in ancient lake beds and subsurface environments. The Spirit rover discovered rocks containing up to 16% magnesium and iron carbonates in the Columbia Hills region of Gusev Crater, indicating significant carbon dioxide was removed from the atmosphere through weathering reactions. Additionally, Mars experiences unique seasonal cycles where approximately 30% of its atmosphere freezes onto the winter pole each year, forming carbon dioxide ice caps. While most of this carbon dioxide sublimes back into the atmosphere during the summer, some becomes permanently trapped in the layered polar deposits, effectively removing it from circulation. Computer models attempting to reconstruct ancient Mars suggest that even with a carbon dioxide atmosphere several times denser than Earth's, Mars would have struggled to maintain temperatures consistently above freezing. This faint young sun paradox, referring to the fact that the sun was approximately 30% dimmer billions of years ago, suggests that additional greenhouse gases must have been present to explain the geological evidence of flowing water. Recent research proposes that transient reducing gases like hydrogen and methane, potentially released during episodes of volcanism or delivered by impacts, might have periodically warmed the planet. Unlike carbon dioxide, which provides consistent but moderate warming, these gases could have generated intense but geologically brief warming periods through specific infrared absorption bands and catalytic effects on atmospheric chemistry. Understanding. Mars's atmospheric evolution challenges scientists to reconsider what makes Earth's climate system so remarkably stable. As paleoclimatologist Dr. James Hansen puts it, Earth's climate stability isn't a coincidence. It's the product of interlocking geological and chemical cycles that have regulated greenhouse gas concentrations within life-sustaining boundaries for billions of years. The lesson of Mars is clear. For long-term habitability, a planet requires not just the right initial atmospheric composition, but also the geological machinery to regulate it across enormous timescales, adapting to changes in solar output, orbital variations, and other perturbations that would otherwise drive the climate toward uninhabitable extremes. Between approximately 3.7 and 3.5 billion years ago, Mars underwent a profound transformation. This relatively brief window in geological terms marks the transition from what planetary scientists call the Noachian period, characterized by abundant surface water, into the drier Hesperian era. Understanding this pivotal transition provides crucial insights into planetary tipping points and climate system collapse. The geological record preserved on Mars reveals a dramatic shift in surface processes during this time. Earlier Noachian terrains show extensive networks of valley systems, delta deposits, and potential shorelines, consistent with persistent surface runoff and stable bodies of water. Later, Hesperian features display dramatically different characteristics: enormous outflow channels suggesting catastrophic flood events, widespread volcanic plains, and surface deposits rich in sulfates and other evaporate minerals indicative of increasingly acidic, briny water bodies. What we're seeing is essentially the death spiral of a habitable planet, explains Dr. Robin Wordsworth of Harvard University. The geological features tell us about a world transitioning from Earth-like conditions to something progressively more alien and inhospitable. Data from the European Space Agency's Mars Express mission has identified deposits of clay minerals, phyllosilicates, primarily in the oldest Martian terrains. These minerals require prolonged exposure to neutral pH water to form. In contrast, younger terrains contain abundant sulfate minerals that typically form under acidic conditions. This mineralogical shift provides a chemical fingerprint of Mars's changing environment, from neutral, potentially life-supporting water bodies to increasingly acidic, briny environments hostile to most forms of life as we know it. What triggered this relatively rapid transition? Current evidence points to a perfect storm of interrelated factors. By this point in Martian history, the global magnetic field had already collapsed, leaving the atmosphere vulnerable to solar wind erosion. Simultaneously, Mars' internal heat engine was winding down, reducing volcanic outgassing that could replenish atmospheric gases. Analysis of zircon crystals in Martian meteorites suggests that heat-producing radioactive elements became increasingly concentrated in the crust rather than the mantle, further reducing internal heat flow. Without sufficient internal heat, Mars' mantle cooled and stiffened, preventing the development or continuation of plate tectonics. Unlike Earth, where moving plates constantly recycle the surface, Mars developed what geologists call a stagnant lid tectonic regime. This lack of crustal recycling prevented the development of the long-term carbon cycle that helps regulate Earth's climate. The Mars Reconnaissance Orbiter has identified numerous ancient impact craters dating to this transitional period that show evidence of once containing lakes. These crater lakes appear to have been disconnected from each other, suggesting that by this time, Mars had lost its connected hydrological system of rivers and oceans, instead developing isolated bodies of water that eventually evaporated completely. Evidence from the Curiosity rover's exploration of Gale Crater reveals that this transition was not smooth, but punctuated by fluctuations between wetter and drier periods. Layers within sedimentary deposits show alternating patterns of lakebed sediments and desiccation features, suggesting that Mars may have experienced cyclical climate variations, potentially driven by changes in its orbital parameters or episodic volcanic activity. What's particularly fascinating about this transition period is that it wasn't just a simple linear drying, notes Dr. Ashwin Vasavada, Curiosity Project scientist at JPL. The evidence suggests Mars underwent climate oscillations, with conditions sometimes improving temporarily before the ultimate slide toward the current cold, dry state. Perhaps most intriguingly, this critical transition coincides with the period when evidence for potential microbial life would have been most abundant on Earth. Fossil stromatolites and other biosignatures in Australian rocks, dating to 3.5 billion years ago, confirm that life had taken hold on our planet by this time. If life ever evolved on Mars, this transition period represents both the most promising window for its emergence and the beginning of increasingly hostile conditions that would have challenged its survival. The most compelling lesson from Mars' critical transition may be that planetary habitability can persist for hundreds of millions of years before collapsing relatively quickly when key stabilizing mechanisms fail. Complex systems like planetary climates can maintain equilibrium despite ongoing stresses, until they reach tipping points beyond which new, often inhospitable equilibria establish themselves. Recent climate modeling suggests that positive feedback loops accelerated Mars' transformation. As the atmosphere thinned, less greenhouse warming occurred, lowering surface temperatures. Colder conditions caused more carbon dioxide to freeze at the poles, further thinning the atmosphere. Meanwhile, as liquid water became scarcer, water-dependent weathering processes that could have sequestered additional carbon dioxide in rock formations diminished, removing another potential stabilizing mechanism. The story written in Mars' geological record serves as both historical document and cautionary tale, revealing how even planets with substantial water resources can undergo fundamental climate transitions when critical planetary systems fail or become imbalanced. While Mars gradually surrendered its water to space and its subsurface, Earth developed into a surprisingly resilient hydrological system. Our planet has maintained liquid water oceans continuously for over 4 billion years, despite experiencing asteroid impacts, massive volcanic eruptions, and variations in solar output that could have potentially pushed the climate toward uninhabitable extremes. This extraordinary stability demands explanation. Earth's water retention success story begins with several fundamental advantages. At roughly 9.5 times Mars's mass, Earth's stronger gravitational field makes atmospheric escape inherently more difficult. Calculations show that water vapor in Earth's upper atmosphere would need approximately 30% more energy to achieve escape velocity compared to Mars. But gravity alone doesn't explain Earth's hydrological persistence. Venus has nearly identical gravity, yet became a scorching desert world. More crucial than gravity is Earth's persistent magnetic field, generated by the circulation of molten iron in our outer core, a process maintained by Earth's greater internal heat. This invisible shield deflects the solar wind and prevents the kind of atmospheric stripping that ravaged Mars. Magnetometer. Readings from satellites like the European Space Agency's cluster mission have directly measured how this field redirects charged particles that would otherwise collide with and erode our atmosphere. Our magnetic field is Earth's first line of defense, explains Dr. Fran Bagenal, space physicist at the University of Colorado Boulder. Without it, we'd likely see atmospheric erosion rates at least 10 to 100 times higher, potentially depleting significant portions of our atmosphere over geological timescales. Equally important is Earth's position in the Goldilocks zone around our Sun, neither too close nor too far for liquid water to exist at the surface. This position allowed Earth to avoid the runaway greenhouse effect that transformed Venus, where water vapor, itself a powerful greenhouse gas, accumulated in the upper atmosphere, trapped heat, increased evaporation, and created a self-reinforcing cycle that eventually vaporized any oceans Venus might have once possessed. But simply being in the habitable zone isn't sufficient for long-term stability. Earth developed several interconnected cycles that function as thermostats, regulating surface conditions despite various perturbations. The water cycle itself acts as a stabilizer, with increased evaporation creating clouds that reflect sunlight, Cooling the planet. The silicate weathering cycle removes carbon dioxide during warm periods and allows it to accumulate during cooler periods, counteracting temperature swings. Perhaps most remarkably, Earth developed biological systems that began influencing planetary chemistry on a global scale. The Great Oxygenation Event, approximately 2.4 billion years ago, driven by photosynthetic cyanobacteria, fundamentally altered Earth's atmosphere, eventually creating the ozone layer that protects surface water from ultraviolet photodissociation. Later, the evolution of land plants further moderated the carbon cycle by accelerating weathering processes. Life doesn't just adapt to planetary conditions, it helps create them, notes Dr. David Catling, astrobiologist at the University of Washington. Earth's biosphere has been an active participant in maintaining habitable conditions, a partnership between geology and biology that Mars never developed, at least not at a planetary scale. Earth has also benefited from several geological features absent on Mars. Plate tectonics continuously recycles carbon and other elements through subduction and volcanic outgassing. The presence of large continental landmasses creates diverse environments and weather patterns that distribute water across the planet. Deep ocean basins serve as vast reservoirs that buffer the system against perturbations. Even if surface conditions temporarily become hostile to life, the deep oceans can preserve biological communities that later repopulate the planet. Plate tectonics particularly distinguishes Earth from Mars. While Mars developed a thick, rigid crust that prevented crustal recycling, Earth's lithosphere separated into moving plates that interact at boundaries. This system not only regulates the carbon cycle, but also generates new continental crust through processes like volcanic arc formation, creating the land masses necessary for Earth's diverse environments. One often overlooked factor in Earth's stability is our unusually large moon, formed from the debris of a Mars-sized planetesimal impact early in Earth's history. The moon's gravitational influence stabilizes Earth's axial tilt at approximately 23 degrees, preventing the wild oscillations that characterize Mars' obliquity, which can vary from 0 to 60 degrees over millions of years. These Martian obliquity oscillations drive extreme climate variations, as the distribution of solar energy across the surface changes dramatically. Earth's climate has changed substantially throughout geological history, explains paleoclimatologist Dr. Maureen Ramo of Columbia University's Lamont Doherty Earth Observatory. We've had ice ages and hothouse periods, but the remarkable thing is that despite these fluctuations, liquid water has remained continuously present somewhere on the surface. That speaks to extraordinary systemic resilience. The contrast between Earth and Mars demonstrates that planetary habitability depends not just on initial conditions, but on self-reinforcing systems that can maintain stability over geological timescales. While Mars started with considerable water resources, it lacked the integrated geological, atmospheric, and eventually biological systems that allowed Earth to weather cosmic challenges while keeping its precious oceans intact. The divergent fates of Earth and Mars offer profound insights as we extend our gaze to distant solar systems. With over 5,000 confirmed exoplanets and thousands more candidates awaiting verification, astronomers are increasingly focused on identifying potentially habitable worlds. The Mars-Earth comparison provides a crucial framework for understanding which distant planets might not just temporarily host water, but maintain stable hydrospheres over the multi-billion-year timescales, potentially necessary for complex life to evolve. Current exoplanet detection methods primarily identify planets based on their size, mass, and orbital parameters, enough information to determine if they reside in their star's habitable zone. However, the lesson from Mars is clear. Location alone doesn't guarantee long-term habitability. Next-generation observatories like the James Webb Space Telescope, JWST, are now beginning to characterize exoplanet atmospheres, looking for water vapor and other biosignature gases that might indicate Earth-like conditions. When we look at exoplanets, we're essentially seeing snapshots in time, explains Dr. Victoria Meadows, principal investigator for NASA's Virtual Planetary Laboratory. The challenge is distinguishing between planets that are transiently habitable, like Mars was, and those with the necessary feedback systems to maintain habitability over billions of years. The Mars-Earth comparison suggests several key indicators astronomers should seek when evaluating exoplanet habitability potential. Planetary mass appears particularly crucial. Planets significantly smaller than Earth may lack sufficient gravity and internal heat to maintain both atmospheric retention and the geological activity necessary for long-term climate regulation. Current models suggest that planets with masses below approximately 40% of Earth's mass, about 4 times Mars's mass, may struggle to maintain the geodynamic processes needed for sustained habitability. Magnetic field detection represents another frontier in exoplanet characterization. Although directly observing exoplanetary magnetic fields remains challenging, astronomers have recently developed techniques to detect their signatures through star-planet interactions. The auroral emissions generated when stellar winds interact with magnetospheres produce radio signals that next-generation facilities like the Square Kilometre Array might detect, potentially allowing scientists to distinguish between magnetically protected and unprotected exoplanets. The Mars comparison also highlights the importance of atmospheric composition over mere presence. Future observatories will need to characterize not just the existence of atmospheres, but their specific molecular constituents and their vertical distribution. Planets with atmospheres consisting primarily of carbon dioxide may indicate stalled geological evolution similar to Mars, while the presence of substantial oxygen or methane might suggest active biological processes similar to those that have helped stabilize Earth's climate. What we're learning by comparing Earth and Mars is that habitability isn't binary. It exists on a spectrum of robustness and longevity, notes Dr. Natalie Cabral, director of the SETI Institute's Carl Sagan Center. Some planets may briefly pass through habitable phases, while others develop the self-regulating systems needed to remain habitable despite external perturbations. This understanding has profound implications for estimating the frequency of life-bearing worlds in our galaxy. If Mars-like planets, initially promising but failing to develop long-term stability, are common, then the number of planets currently supporting life may be significantly lower than estimates based solely on habitable zone statistics. Conversely, if most Earth-sized planets in habitable zones develop the geological and atmospheric feedback systems Earth possesses, the galaxy may contain many more biospheres than previously estimated. Beyond exoplanet science, the Mars-Earth comparison provides valuable perspective on our own planet's future. Earth has maintained remarkable climatic stability despite numerous challenges throughout its history, but this stability shouldn't be taken for granted. Human-driven increases in atmospheric greenhouse gases are now causing changes at rates unprecedented in geological history, potentially bypassing some of the negative feedback mechanisms that have historically regulated Earth's climate. Earth's resilience is impressive but not unlimited, cautions Dr. Catherine Richardson, leader of the Sustainability Science Center at the University of Copenhagen. The Mars comparison reminds us that planetary systems can reach tipping points, beyond which new equilibria establish themselves, potentially ones less conducive to complex life. Understanding exactly how and why Mars lost its habitability potential, while Earth maintained its life-supporting systems, provides context for humanity's role as planetary stewards. Our species has become a geological force capable of altering atmospheric composition, land surface characteristics, and hydrological cycles at a global scale, inadvertently assuming control over some of the same systems that differentiate our thriving world from our desiccated neighbor. The ultimate legacy of comparative planetary studies may be wisdom, recognizing both Earth's extraordinary resilience and its fundamental vulnerabilities. By studying how Mars lost its oceans while Earth kept theirs, we gain insight into the delicate planetary balancing act that has allowed our world to remain continuously habitable for billions of years, and the responsibility we now bear to preserve those life-sustaining systems for future generations. The twin planets that once mirrored each other now offer contrasting futures. Mars represents what happens when planetary systems fail, while Earth demonstrates the magnificent potential of a world where geology, atmosphere, hydrosphere, and eventually biosphere evolve together into a remarkably durable, self-regulating system. As we contemplate humanity's future, both on Earth and beyond, this cosmic perspective may prove to be one of the most valuable scientific insights our species has ever gained.